What we're going to look at here is similar triangles. So similar triangles are triangles where 3 angles in those triangles are the same, but the side lengths are different. So it doesn't matter what the side lengths are, as long as 3 angles are the same, then we have similar triangles. The side lengths are all scaled by the same value though. And so we'll explain what that means in a moment. So in this first case here, we got 2 triangles, A, B, C, and D, E, F. And I had originally not marked these as X, but again, as I mentioned in the previous video, I unfortunately did not record any audio because my microphone wasn't working, so I had to redo all these videos. But here I have 2 triangles, right angle triangle, the dot, the 90-degree angle, and then this angle B. Here I have the same idea, dot, 90-degree angle, and then angle E. These 2 angles are the same, but it says I need 3 equal angles. Well, what are these angles? Well, they must be the same because the sum of all the angles in a triangle is 180. And this plus this is the same as this plus this. So this must be the same remaining value. So these are the same angle as well. So why are these the same? Well, angle A equals angle D. Angle B equals angle E. And angle C equals angle F. So why are they similar triangles? 3 angles all match. Okay, so as long as the 3 angles are matched up there, we got similar triangles. It doesn't even matter if I took this triangle and spun it around so it was up like this, it would still be a similar triangle as long as the 3 angles are the same. Now in the next part here, I got the situation where I got this angle A down here, and then I got 3 triangles sharing angle A right here. I got this triangle, the little one, I got the middle one, and then I got the big one. All 3 of these triangles, why are they similar? Well, there's a couple things you can do. One, again, just as before, they all have this same angle, plus they all have a 90, thus the other angle is the same. And we could say they're all the same because the 3 angles match up. Or we could look at the scaling in size. So this first triangle, this is 1, 2, and then 3 in height. So this is twice as big as this one. Well, this side here goes from 2 to 4. This whole side here would be 4. This whole side would be 2 times root 5. So that would be twice as big as that. Scaled the same. This would be 3 times as big as the first one. This is 6, 3 times as big as 2. This is 3 times root 5, which is 3 times as big as root 5. So this as well is the similar triangle. So all 3 triangles are similar because they when all 3 sides are multiplied by the same number, it matches up with each one. So where does this all go? How do we apply this kind of thing? Or sorry, this is the sides are multiples of a constant value. Use that as an answer there. Now, we can use these to solve problems. We can be given situations like, say you wanted to get the height of a tree. Not necessarily the most convenient thing to do is to climb up that tree, especially if it's a pretty tall tree. Safety concerns and all that. Maybe you're like me and not very good at climbing trees. You don't want to fall out and hurt yourself. So how can you get the height of a tree without climbing that tree? And what you can do is use the idea of similar triangles. So here is the setup for this question. And I have a table setting this up. So I'm making a table where I'm comparing the height of the guy to the height of his shadow, or the length of his shadow. When you're outside, maybe I should explain this first. When you're outside and the sun is shining down on you and you're near something, the sun will be hitting you both at the same angle relatively. For all our purposes, it's the same angle. As long as you're near each other, if you're 100 miles away, it's going to be different. But if you're, within a few meters, you're probably going to be fine. So the angle here, this angle, call it say theta, is going to be the same. They're both right angle triangles, and thus we have these similar triangles. So that's why we can set this up, because they are similar triangles. And so what we're going to do here is we got this shadow of 25 and the height of the tree. the shadow 4 meters, and the height of the guy being 1.9. So we're looking for the height of the tree. So one fraction will be set up for the tree, one fraction set up for the guy, and these will be our ratios that we're comparing. I'm looking for the height of the tree, so I put that up here. That means I got to put the height of the guy on top as well. The heights both the heights have to be here, and then the shadows have to be on the bottom. The shadow of the guy, the shadow of the tree. If I was looking for the length of the shadow, then I would put the shadows on top and the heights on the bottom. But the tree goes in one fraction, the guy goes in the other fraction, and as long as the corresponding sides, so the same height, both of these are the heights, both of these are the shadows, then we're good here. Okay, so they have to stay together in that same setup. And then once we do that, we can just do our calculations here. We do 1.9 divided by 4, which is 4.7 or 0.475. It's going to be h over 25. And then we move that 25 over and multiply. And then we get 11.875 is the height, or about 11 meters and 87.5 centimeters. There's the height of our tree. So we set up our scenarios by looking at, in the case of something where there's a sun shining and there is light, the sun rays coming down, this is the setup for it. As long as we have two triangles, so all you need to do is make sure that you have two similar triangles. In the cases of our similar triangles, we're going to be working with right angle triangles, so they just need one other angle to be the same, then you'll know they're similar. And again, set up the matching sides on the same level of the fraction, top or bottom. And I think that's about it for this one. So that's similar triangles. And then you can try some of those practice questions with these.